Hello, everyone. This is the lecture for section 2.4 for Math 210, continuity. So one of the things that we use the limit for in sort of the greater picture for calculus is to define something called continuity, okay? And it's a property that is super important when we start looking at other functions later on in the calculus course, okay? So let me just go ahead and jump in to what continuity is, okay? And the way I'm going to do this is I'm going to go ahead and first define it, okay? And then we'll play around with the meaning of it, okay? So we say that a function is continuous, okay, at a point x equal a, right, if and only if these three things are satisfied, okay? If and only if these three things are satisfied, okay? And it is discontinuous if it fails one of these three things, okay? First of all, number one, f of a has to be defined, okay? The second of all, f of the limit as x approaches a of f of x has to exist, right? So keep a track of this, right? This one says that the function has to be defined. This one says that the limit has to exist, right? And this one says that both 1 and 2 have to be equal, okay? So then if you look on a graph, right? So I'm going to go ahead and graph something here. I'm going to, okay, here's f of x, right? And we want to approach a value right here. Let's say that, right? Dot, 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 a. In this case, I am calling this f of a, okay? So then that means this point is a comma f of a, okay? Okay, so let me go through these really quick, all right? The first one is saying that f of a has to exist. That is, right, we've seen functions that have like an open dot, right? Number one says that that is not the case. We do not have an open dot there. This function is actually defined there, okay? Second thing, number two, right? When we say number two, we are saying that the limit, right, as x approaches a of f of x exists. So that means if we head toward this point from the positive end, right, and if we head toward this point from the negative end, right, it's got to approach a particular value. It's got to approach something, right? And I don't know why it disappeared, but it's got to approach something. Yes? Okay? That was the idea of a limit from the previous section, right? And then, like I said, number three says that both of those things, right, have to be equal. So your function's got to approach from the left, from the right, the exact same point, and it must equal the function value at that point. Okay? And then we say a function is discontinuous, right, if it fails to meet one of the three things. Got it? Okay. This is the actual definition of continuous. Okay. You will hear this a lot. There is a functional definition, basically like a sort of like a quick and dirty way of determining if you have a function that is continuous or not. Okay. And that is this right here, that a function is continuous if you can draw the function, right, without picking up the pencil, okay? The second you pick up the pencil, right, wherever you picked up the pencil, that is where the function is discontinuous, okay? Okay. The actual bona fide proof, the mathematical proof for continuity is much harder than this. So for now, right, this is going to be what we're going to be using for now, okay? However, I will have you guys all practice this, right? That if something is continuous, all three of these are satisfied, and if something is discontinuous, one of these three things is not satisfied, okay? So, first of all, let's go ahead and do an example. So there's this graph, okay? Graphs that are set up like this, they are called piecewise functions, okay? Basically saying this, right? That if your x value fits here, then you are graphing this. If your x value fits here, you are graphing this. If your x value fits here, you are graphing this. And if your x value is here, you are graphing this, okay? Now, you can go ahead and attempt to graph it. If you take a look over here to the, what is that, to the right of the notes, I put the graph of the examples already, so you don't have to if you don't want to, okay? What I'm gonna do is I'm gonna open up Desmo since I have it set up already, okay? Almost, okay? Here it is. This is the graph that I need, okay? So what I'm gonna do is I'm gonna come down here and I'm gonna get the snipping tool. There it is. I'm gonna take a picture of this and I'm just gonna superimpose it over the top of our thing, okay? Keep this link handy because I will be asking you, and your online homework will be asking you to create piecewise functions pretty darn soon, okay? So what I'm gonna do, I'm gonna try to make this smaller so we can all see it, and I don't wanna move anything. There we go. Now I'm gonna stretch this out so that it covers the, boom, there we go. So there's this graph, okay? There is one point that is missing, okay? I do wanna point it out, okay? It's these three right here, okay? If it's less than, strictly less than -2, then it's the yellow minus 2x minus 4. If it's equal to 2 exactly, it's going to be equal to -2. So this is the thing that's sort of missing, okay? In the sense that this is what's going to happen, that you're going to go, this point right here is going to have an open circle, and then there's going to be a random dot down there, okay? So the graph, this graph is actually defined, right, at that point, not here, okay? All right, so now, let's move on to the questions, yeah? So I'm gonna drag this over here. I'm gonna open up, there we go. I'm gonna make that, okay. So, A was graph it. We used Desmos, so we're good there, okay? B, precisely justify each discontinuity, okay? So remember how I said, right? And actually I'm gonna have to zoom in, or zoom back up to our example. Wherever you pick up your pencil, right? That is where your function is discontinuous, okay? If you can draw it without picking up your pencil, wherever that is continuous, okay? So if you take a look, right? I can draw this segment all the way down to maybe about here, right? I can draw it all the way down to there without picking up my pencil, right? So this point right here, and I'm going to highlight it in pink, this is going to be a discontinuity, okay? Again, from here on this way, I can draw the graph without picking up my pencil. Right here, right? Here's another spot where it has an open circle, right? This is where I have to pick up my pencil, right? This is a spot where it's discontinuous, and then I keep on going this way. There's no problems after that, right? So there are 2 points where they are discontinuous, okay? 2 points. So it's discontinuous. And I'm going to refer to them at x equal, what's the x value there? -2 and that 0. Okay, so let's do x equal -2. Okay, so first of all, if you've got it at the ready, there were the 3 conditions at the very beginning of the section, right? It's discontinuous because it's violating one of those 3 things, right? One of those 3 conditions. We got to go find which one, Okay, so the three that we have are this, right? That f of a, well, f of a is defined, right? Whoa. The limit as x approaches a of f of x, right, exists. And three, the limit as x approaches a of f of x has to equal f of a. These were the three conditions, right, in order for something to be continuous, right? Since we can see it is discontinuous because we have to pick up our pencil, right? It's got to violate one of these three things, okay? So these are the three conditions. I'm gonna go ahead and write our answers in green or red so that we can keep a track of what's yes and what's no, okay? So according to my definition, at -2, right, f of a is defined. That's this bit, okay? So we can go ahead and say, right, that f of a, in this case f of -2, right, is equal to -2. So this one checks out. Got it? Okay. Number two, okay, that the limit has to exist. So if you do the crawling, you know, follow the breadcrumbs from the left and follow the breadcrumbs from the right, right? You can see that it's heading to the same point. It's heading toward the y value, in that case is 0, correct? So we have 2. 2 is telling us that the limit as x approaches 2 of my f of x, that is equal to 0. This one checks out. Okay? But the last one, okay? The last one said that both of these had to be equal. One of them is equal to -2, the other is equal to 0, right? So I'm going to put it right here, right? -2 does not equal 0. This one's the one that screws it up. So for this function, right, our function f of x is discontinuous at -2 because of this one right here, because of this last condition. This one is the one that's violated. Okay? Okay, let's do it again for x equals 0. Okay? So I'm going to write the 3 again, right? F of a is defined. The limit as x approaches a of f of x exists, right? And the last one is the limit as x approaches a of f of x is equal to f of a. Okay, so now let's go back to our graph, right? Okay. Okay, we are looking at this particular right there, right? Okay, let's look at what happens. Is f of a defined? And according to this thing, yes, it is. It is defined by the third equation. So I can plug it in, right? And I should be able to get a value. Okay, so then in this case, if you take a look at the graph, right, it's telling us that f of 0, I'm going to put it over here in green again, right? F of 0 is equal to 4. So there's no problem with that condition. Okay? Okay. Next one down. The limit as x approaches a of f of x must exist. If you take a look at it, you guys see what's going on now, right? So if we approach 0 from the left and from the right, notice what happens, right? This one shoots upward, right? But this one shoots to -4. Or sorry, +4. Right? So I'm going to scooch this over a little bit. There we go. So I'm going to do the limit as x approaches 0 from the positive of f of x, right? is equal to positive infinity, right? The limit as x approaches 0 from the negative of f of x, that is equal to 4, right? These two are not equal. Those two are not equal. And we only just need to make sure that one of them is not satisfied, right? Since both of these are not equal, this does not exist, right? Okay, that's it. We determined which one of the three conditions is not satisfied. Okay? Okay. Last part of our question. On what intervals is f of x continuous? This works out the same way as we did with the domain. Okay? When we did domain, right, we grabbed the values that didn't work, right? Kick those out. Everything else is fair game. Same thing here. We are going to collect all the values that are not continuous, kick those out, everything else is fair game. We already found the points where it's discontinuous. So negative infinity to -2, union -2 to 0, union 0 to infinity. There we go. That is those are our intervals where it is continuous. All right. We're moving right along. Okay. In general, there are three types of discontinuities. There is, you've heard of this one before, a removable discontinuity. Okay, I'll cover that one in a second. We have what's called a jump discontinuity. Okay, and then we have infinite discontinuities. Okay, and you've seen all three of these. We just haven't formally defined them using our calculus yet. Okay, a removable discontinuity is one of these, where you have a graph that heads somewhere, and then all of a sudden you have an undefined point, but then it keeps going in that same direction, right? If you guys remember what a hole was, right? This is the reason why we call it a removable discontinuity. And the reason why we call it the removable discontinuity is because we can remove the discontinuity if we just filled in the point. Done. That's how we remove the discontinuity. Okay? So whenever you have the open dot like that, whenever you have a hole, right? This is why we call it a removable discontinuity. Okay. Jump discontinuities. Okay. Those are the ones that do this. You have a graph that does something and then it stops and then continues on somewhere else like this, right? This is the problem spot right here. Okay. They're defined by a jump of some sort. Okay. And then the last one, the infinite discontinuities, is when you have something that looks like an asymptote. So for example, you can do a whoosh, right? And then another whoosh like this, and then another one that goes like this. If you have a graph that does something like this, which they exist, they definitely do, right? Right here, that's a problem. That is an infinite discontinuity, okay? And then this is a problem as well. It's an infinite discontinuity as well. Even though both the infinities are going toward the same infinity, right, the positive infinity, right, we needed to go to a specific value. That's what the three conditions for continuity are, right? Since we don't have that, that's it, right? Okay. Moving right along. Well, before we do that, and then the last big definition here. We know what it means to be continuous on a point, right? At a point x equal a. That's the three conditions, right? A function f of x is continuous on an interval from a to b if it's continuous at every point. So if you can prove all three of those conditions for every single point if inside a to b, you have something that is continuous on an interval a to b. Okay? Okay. I've got a couple quick checks here. Like I said, we'll do these during class. You can try them out yourself. Try to use Desmos. If you are going to try these, try to use Desmos to graph these to determine what kind of discontinuity you have and over what strip it is continuous. Okay? Moving right along, there's a bunch of theorems here that I'm going to throw out at you. Okay? Number one, okay? Suppose f and g are continuous functions at a value x equal a with a constant number c, okay? Then you can take it as fact that all of these are continuous, okay? That if you have two continuous functions, okay, let me go through them really quick, right? That if you have two continuous functions, the addition or the subtraction of two continuous functions is continuous. The multiplication of two continuous functions is continuous. The division of two continuous functions is continuous, provided that the bottom is not equal to 0, okay? Funky things happen when you do that. And then the last one is when a constant value times a continuous function is continuous as well. Okay? Okay. This is a theorem. I think I need to add this in because it's not in your textbooks. And it's a very important statement to say, especially right now since we're doing calculus in an accelerated sense, right? Without proof, you can take this as a fact at this point, right? All of these types of functions are continuous over their entire domain. Okay, so trig functions, so sine, cosine, tangent. We haven't covered those yet, but I should put those in here now. Trigonometric functions, polynomial functions, the ones that we were just doing in section 3.2 to 3.6 from our pre-calculus book, right? Exponential functions and logarithmic functions are all continuous. So if you see those problems in your online homework, you automatically can assume that those are continuous. You don't need to prove them to me. Okay? Okay. Next up. Suppose you have a function that is continuous at L, right? And the limit of g of x is L, okay? Then the limit of the composition is equal to the function of the limit, right? Which is equal to f of L. We haven't covered compositions yet, but this is basically saying, right, that if you have a continuous function inside of another continuous function, it is also continuous. That's actually the theorem right below it, okay? If you have the composition of if you have one function inside of another, we also can call that continuous, okay? All right. Moving right along. So for now, I know I'm throwing around a lot of math that we have not seen yet. Some of you might have seen it in high school, right? But I am acknowledging, right, that a lot of you have not seen these functions yet, okay? Do not worry about it. We are going to concentrate on specifically polynomials for a little bit, and then we'll graduate up to the bigger types of functions, so exponentials, the logarithmic, and the trigonometric functions, okay? Okay, but for now, I want everybody just to look at the conceptual idea, right, of continuity, okay? And we're going to try to use that within the problems that I'm going to be giving you, okay? There is a quick check right here that shows sort of gives you a good feeling for why we need continuity, okay? And this example deals with tax brackets, okay? The QR code is there. It'll pop up a brand new graph for everybody. It's a piecewise function, okay? So I want you guys all to try this out. Everybody is going to be doing the exact same quick check. Don't entirely like it. I'd rather you guys have like 3 or 4 quick checks to try. But in this case, there's just the one. We'll come back together and talk about it, okay? And I believe, not yet. Aha, not yet. Okay. I thought the section was over. Okay. There's a one big heavy hitting theorem, the intermediate value theorem, okay? And this one requires us to use continuity, and it's really important in the higher level maths, okay? If you ever study math for the rest of your life, this theorem is used repeatedly everywhere, okay? All right, so let me read it out, and then I'm going to turn it into the picture, okay? So suppose that you have a continuous function, f, on a closed interval, ab, and you let n be any number between f of a and f of b, right? Where f of a does not equal f of b. Okay? Then there must exist a value c in AB such that f of c is equal to that value n. Okay? I know that sounds complicated. Okay? So that's why I want to turn it into, this is one of the ones where if you understand the picture, the intermediate value theorem makes complete sense. Okay? So the first thing I'm going to do, right, it says there that I'm supposed to pretend, right, that I have a continuous function f. So I'm going to grab this, there's a continuous, so we're still using the working definition of continuity. Does that make sense? Okay. And suppose that I am going to look at this, oh, crap. There we go. Suppose that I'm going to be looking at this from a value A to a value B, right? We know that this is f of A, okay? And this way up here, right here about, let me see, yeah, right there, yep. Oh man, there we go. Okay, and I'm gonna actually draw this line down and then this one too. There we go. Okay, so we have two intervals that I want you guys to sort of dwell on here, right? We have this interval from A to B, right? And then we have this interval from f of A to f of B. Okay? Okay. I'm going to now do this tail end that's right here. Okay? Intermediate value theorem states that I am guaranteed a number C in A to B, inside this strip right here, right? Such that if I plug in C, I'm going to make it orange in this case. If I plug in a value C, there's got to be, well, sorry, the other way around. Ha. I did it the wrong way. Okay. And suppose we chose an n value. There we go. I jumped the gun a little bit. Suppose I chose an n value in between f of A and f of B, right? Then I am guaranteed this value down here. So I'm going to follow this over to here, and down to here, C. I'm guaranteed this value, such that, let me actually, come on. I don't know why my eraser is not working. C, comma, f of C is equal to n. I am guaranteed that this is going to happen. I am guaranteed that this is going to happen right here. Okay? This result cannot happen unless your function is continuous. Okay? Okay. Last thing, okay, is an example. I want to do an example with the intermediate value theorem. And this is actually a pretty legit way, albeit it's a very rudimentary, a very simple example of how the intermediate value theorem is used in application, right? But it still gets the point across, okay? So I'm going to use the intermediate value theorem to show that f of x, this function right here, has a root. So if you guys remember what a root is, x-intercept. Okay? We are going to show that this thing has an x-intercept. Okay? And in particular, we're going to show that it is in here. Got it? Okay. So the first thing that we have to show, according to intermediate value theorem, is that my f of x is continuous, right? So look at what I'm going to do here, right? So cosine of x, that is continuous. I gave you that in the theorem, right? So therefore, 2 cosine of x is continuous, right? Minus 3x is continuous. Whoops, did it wrong. Over here, I'm going to do minus 3x continuous, right? Both of these together tell me, right, that f of x, because it's the difference between these two, right? F of x is continuous. Okay, we have that. Now, how do we actually use the intermediate value theorem? Okay, here we go. So I'm going to scroll down a little bit. I'm going to compute two values, f of 0, and I'm going to throw them into Desmos, right? When you do f of 0, that is going to be 2 cosine of 0 minus 3 times 0. That is equal to 2. And f of 1 is equal to 2 cosine of 1 minus 3 times 1. That is equal to negative 1.919. Okay, I'm going to draw a graph here. Okay, and I want you guys, we don't need to know, this is the nice thing, we don't need to know what this function looks like. Okay, but we know two things, three things for this thing, right? First of all, at 0, it is positive 2. So it's up here. So 1, 2, 1, 2. At 0, it's up there. At 1, it is negative 1 point almost 2, right? So I'm going to do 1, 2 down here somewhere. So this is going to be 1 comma negative 1.919. Let me move that up a little bit. Uh-oh. Uh-oh, there we go. Okay. One of the points for our function is right here, up there. The other point for our function is down there. And in particular, we have this result, this big result for our function. F of x is continuous. So that means between these 2 points, I should be able to draw a line without picking up my pencil. You guys see that? To the other point. That's what it means to be continuous. Right? There I did it. That is there, right? It doesn't matter how you draw that continuous line, so long as it's continuous. So long as you draw from one point to the other without picking up your pencil, that function is continuous, right? Now, what I want everybody to see is this. We can't do that unless we cross the x-axis, right? That right there is the x-intercept. And that right there is our proof, this right here. We cannot draw a continuous function, right, from this point up here to this point down here without crossing the x-axis. Hence, we must have a root. We must have an x-intercept. Okay, now, we know that one exists, right? We just don't know what that value is, okay? And that's fine. The intermediate value theorem just said that one exists, and that's fine, okay? If we really do want to find it, we have to go and actually throw it to a computer for it to actually give me a numerical answer, okay? All right, I believe now, is that it? Yup, lecture questions. If you've got any questions on the stuff that I just covered, ask me during our quick check time. Come downstairs to the tutoring center or find me in my office, okay? And we'll go it over, okay? Besides that, happy studying.